The SR-71 Blackbird is one of the fastest planes on Earth. It can go 3 times the speed of sound, or about 2,000 miles per hour. Even though it's a really highly engineered airplane, it has an embarrassing secret. When it sits on the runway and you fill its fuel tanks, they leak. Awkward. Why is that? Well, it turns out that they're actually accommodating for what's going to happen in the air. When the Blackbird moves at 2,000 miles per hour, it gets hot. And things that get hot expand. And actually, this is kind of an interesting aside, but central to our lesson, that expansion does work. When you expand something, that's actually doing work. So you transfer heat to the SR-71 Blackbird, it does the work of expanding all of the different parts of the SR-71 Blackbird, and then the fuel tank stops leaking. So, in this lesson, we'll learn all about the interplay between heat and work, and what's called the first law of thermodynamics. Let's learn. Let's begin by reviewing our lesson objectives. First, we'll introduce the first law of thermodynamics. Then we'll learn to determine the signs of heat and work. And lastly, we'll calculate the change in energy of a system. These giant torches are pretty sweet. It turns out they're heating up air for a hot air balloon. Currently though, the balloon is just sitting on the ground. You see, the heat added to the air ends up doing work to expand the balloon. The thing is, though, that the work you can get done is limited by the amount of heat we add to the balloon. The more heat added, the more work we can do. Eventually, the expansion of this hot air will allow the balloon to take to the sky. This exchange between heat and work and the energy of the balloon is dictated by a fancy equation. This guy. Delta E equals Q plus W. All right, we've looked at enough equations in this class that I think you might just be able to guess what these variables stand for. Why don't you pause the video and guess and see if you can get these right. All right, now let's actually go through them. The W stands for work. And in the hot air balloon example, the work done is kind of interesting. You see, this hot air balloon is expanding. And recall that work is equal to force times distance. Well, as the balloon expands, it's applying a force over a distance. So the expansion of the balloon applies a force over a distance. So this is work, even though it might not look like the other examples of work we've seen in this class. Back to our equation. Q is heat. So for our example with the hot air balloon, the torch is adding heat to the balloon. And then lastly, we have delta E, which stands for the change in energy. This actually is a statement of the first law of thermodynamics. And what it tells us is that the change in energy of a system, that's delta E, is equal to the heat added or lost, plus the work done by the system or on the system. We can state this mathematically or with words. The first law of thermodynamics with words is energy is not created or destroyed, and that's actually summed up here because we can only change the energy of a system by adding heat or removing heat or doing work or having the system have work done on it. So basically this is just saying the change in energy can't be any larger than the heat added or the work done. There's also another interesting implication of this law. It tells us that energy fundamentally can only be transferred as heat and work. So energy can be transferred only by heat and work, and that's kind of surprising. The other thing to realize is that Q could actually be positive or negative. Q would be something heating up if it was positive, and Q would be something cooling down if it were negative. So systems can lose or gain energy by heat. That's also true for our work. Systems can lose or gain energy by work. And so when we use this equation, it's really important that we correctly identify the signs of Q and W. Is something gaining energy as heat or losing it? Is something gaining energy by work or losing it? So it's really important to think about this carefully. We're going to go through a bunch of examples here to help you think about the signs on Q and W. For example, take a process where the system is heated. So in this case, say the hot air balloon is your system. Well, in that case, the balloon is gaining energy by heat, and so we would say it's a positive Q. An example here would be a tea kettle being heated. So here's a tea kettle being warmed up by a hot flame, And that tea kettle is going to gain energy, and so we say that Q is positive. Meanwhile, a system cooling is an example of a negative Q. For example, a hot pie being removed from the oven. This hot pie comes out of the oven and it transfers energy to the surroundings. So that means it's losing energy in the form of heat. We can also transfer energy as work. For example, if work is done on the system increases in energy. For example, when a basketball is blown up. Here we're pumping up a basketball. That's doing work, and as we do that work, we increase the amount of energy the basketball has. On the other hand, work can be done by a system, and there we have a negative W. The system is getting less energetic by doing work. It's using up some of that energy. For example, a car engine piston expanding. Here's what happens. We have an explosion in our piston in our car, and that's going to expand the piston to do work to move the car. So the piston itself is actually losing energy by doing work on its surroundings. Okay, now this can be a little confusing. So don't worry, we're going to look at tons of examples. And this will really help you figure out exactly what we're talking about here with these changes in heat and work. Let's take a look at a cool example. Here is the SR-71 Blackbird we talked about in the introduction. Let's think about what happens as it moves really fast. At Mach 3, the panels on the plane increase in temperature. So is that going to be a change in heat or work? Well, clearly heat, because it's changing the temperature. Now, maybe the slightly harder question. Is this a positive change for heat or a negative change? Well, we know it has to be positive. Why is it positive? Well, the energy of the plane is increasing as it gains temperature. Okay, also, as the temperature changes at Mach 3, the panels on the plane expand, doing work. So the panels are expanding, and that is doing work. The system is doing work on the surroundings, and that means that work is negative. Let's actually apply these rules to solve some problems. All right, let's actually apply the first law of thermodynamics to this situation. This problem says an SR-71 Blackbird absorbs 32,000 kilojoules of heat while the plane's panels expand, doing 200 kilojoules of work on the surrounding air. Well, in these situations, what we should do is write down what heat and work are and pay extra close attention to the sign. So first, let's take a look at Q, or heat. Well, we know it's 32,000 kilojoules. Is that positive or negative? Well, because it absorbs 32,000 kilojoules, it's going to be positive. And I like to actually put the positive sign there. I know that looks a little redundant because our numbers are always positive if there's no sign in front of them. But that's just there to remind us that we actually did think through if the sign should be positive or negative. It's very easy to do these problems and forget to think about the sign. For work, our plane is doing 200 kilojoules of work as its panels expand. That means it's going to drop the amount of energy that the plane has. So that's going to be minus 200 kilojoules. And then we want to calculate our change in energy. This, fortunately, is pretty straightforward once we've assigned our signs. We just need to plug in our Q of 32,000 kilojoules, and then we plug in our work of minus 200 kilojoules. That will give us a change in energy for the plane of 31,800 kilojoules. What that means is, on the whole, the plane increased in energy from that friction of 31,800 kilojoules. This problem says a hot air balloon absorbs 275,000 kilojoules of heat while doing 92,000 kilojoules of work. What is the change in energy of the hot air balloon? Once again, we just need to write down the variables we've been given and assign the sign correctly. So Q, which stands for heat, is going to be positive in this case, 275,000 kilojoules. Why is it positive? Well, the hot air balloon is absorbing that heat, presumably from that torch. At the same time, the balloon is expanding and doing work, which is dropping the energy of that hot air balloon. And so that means our work is going to be negative. That will be negative 92,000 kilojoules. And once again, once we've assigned the signs, then the rest of the work is pretty straightforward. Delta E equals Q plus W, which is going to be equal to 275,000 kilojoules minus 92,000 kilojoules. So what is our change in energy? It's going to be 183,000 kilojoules. So our hot air balloon increased in energy from the torch by 183,000 kilojoules. Okay, now it's your chance to practice. Here, we're just going to identify in each case if we have a change in heat or work, and if it should be positive or negative. Pause the video and decide for each one of these, are they heat or work, and are they positive or negative? Okay, let's go through the answers. A balloon is heated by the sunlight. Well, something is being warmed up, so clearly that's Q, and the balloon is increasing in energy, so that's going to be a positive Q. A toaster warms toast. Once again, the toast is heating up. And since the toast is heating up, it's going to be positive Q. C says water cools in the fridge. Well, now water cooling in the fridge means there's a change in temperature, but it's a drop in temperature. So it's a negative Q. Cement expands in the sun. This is a tricky one because the sun means the cement is warming. And as the cement is warming, it's doing work. This is very much like our example with the SR-71 Blackbird. And so there's both heat and work at play here. So if you just put one, heat or work, pause the video again and see if you can fix your problem. Know that there's heat and work. Decide the signs on both. Well, heat is going to be positive because it's warming up, and work is negative because the cement is doing work to expand. That takes away some of its energy. Lastly, a compressed spring expands. This is a really clear example of work decreasing the energy of a system, because after it expands, it can't do as much work as it could do before. So we have negative work. Let's review what we've learned. First, we introduced the first law of thermodynamics, which says that energy can't be created or destroyed. But also we can state it mathematically as delta E equals Q plus W. Then we learned to determine the signs of heat and work. If a system is gaining energy by heat or work, it's positive. And if it's losing energy by heat or work, it's negative. And lastly, we calculated the change in energy of a system.
Hey, hey.